I want to just say a few words about the magnitude of the equilibrium constant. And this is true for Kp or Kc. The examples given here are for Kc, but it could be a Kp. So magnitude just means the size of K, right? So if you look at this picture, this is an image from your book where the left side of the arrow are very small equilibrium constants. Now these can be as low as 10 to the negative 30. That's a very, very small number. Sometimes you even see 10 to the negative 40, 10 to the negative 50. They can be very, very small numbers. So remember that 10 to the minus 30 would be 0.00000, where you have 29 zeros and then a 1. Okay, so that's a pretty small number. And you can see here that underneath the arrow it says the reaction proceeds hardly at all. That means that at the end of the reaction, when it comes to equilibrium, you still have a large amount of reactants left and not many products have formed. Now, what we say is these reactions with very small values of K, quote, lie far to the left. And that's because the reactants are on the left, and so we would say that they lie far to the left. Now, if you look on the right-hand side with the red, where the K value might be very, very large, again, K can be as small as 10 to the negative 30, but can be as large as 10 to the positive 30. And so that would be a 1 with 30 zeros after it. So that's a pretty large number. And what we say is that these reactions lie far to the right. And you can see just above that arrow that I drew, it says the reaction proceeds nearly to completion. So that means that at equilibrium you have almost exclusively products and no reactants essentially left at equilibrium. Some equilibrium constants have K's near 1, which means that you have similar amounts of reactant and product at equilibrium. Now, so for each of these examples, we can answer the question, does the reaction lie far to the right or far to the left, or neither, meaning approximately equal concentrations of reactants and products. So the first one, Kc of 4.7, that is a K value very close to 1. And so we would say that that one is neither. The second reaction lies far to the right, and that is because it has a K value of 10 to the 4 times 10 to the 45, which is a 4 with 45 zeros after it, which is a very large number, which means it lies far to the right, which means that at equilibrium you're going to have a large amount of copper oxide, not very much copper and oxygen left. The third reaction there, 2 times 10 to the negative 19, lies far to the left. That's a small number, a decimal point with 18 zeros, and a 2, right, is a pretty small number. The reaction lies far to the left. And we often draw the arrows different sizes to signify that the reaction lies far to the right or far to the left. And so sometimes you see equilibrium arrows where the top arrow to the right is much larger than the lower arrow going to the left, or vice versa, and that is an indication using arrows that the reaction lies far to the right or far to the left. The last equilibrium given there, the combination reaction where N2 combines with hydrogen, and that reaction certainly lies far to the left because K is very small. So at equilibrium you'll have very low H4. Now, one other thing, I guess the next little small tidbit of information is how we change the value of K when the reaction changes. So if you look at these two reactions and you compare them and try to figure out how they are related to each other, what you'll notice is that one of them is the reverse of the other. And so reversing a reaction will invert the value of K. And so K of the forward reaction will be 1 over K of the reverse reaction. Now, if we look at these two reactions, we have reactions 1 and 2. When you combine those, that gives you reaction 3. So if you combine them, you'll notice that the NO2 on the right cancels out, the NO3 on the right and the left cancel out, and one of the NO2s on the left goes away. So you get the overall reaction shown at the bottom. So reaction 3 is the sum of reactions 1 and 2. Okay, so here we have our reactions. We know that reaction 3 is the sum of reactions 1 and 2. And if we write the equilibrium expressions for reaction 1 and reaction 2 and reaction 3 and compare them to each other, then first we'll write the K1 expression. And so that's going to be NO3 times NO divided by NO2 squared. K2 expression will be NO2 times CO2 divided by NO3 and CO. All right, so this is good practice for writing equilibrium constant expressions. So make sure that this is what you would get for K1 and K2 given these two reactions above. Remember that this stoichiometric coefficient, the 2 up here on the reactant side, becomes the exponent. And then we write the equilibrium constant expression for the overall reaction, K3. And we can prove that this is the combination of these two. It's the product of K1 and K2. So if you take the product of K1 and K2, you multiply them together, then remember what you have NO3 in the numerator and in the denominator, so that goes away. And then you have 1 NO2 in the numerator here, but you have 2 of them in the denominator there, so this 1 up here goes away, and then that 2 becomes a 1. Right, so we're going to cross off things that cancel out, NO3s and 1 of the NO2s, and you get that K3 is the same as K1 times K2. All right, that's what we decided. So the way you'll use this information is if I give you a value for K1 and K2, then you can multiply them together and that gives you the value for K3. Okay, so we've talked about this one. Let me scroll through it. K3 is the product of K1 and K2, so we know that that is true. Now, also, there's one other kind of manipulation you can do. How are these two reactions related to each other, right? So we have 2 moles of NO2, the first reaction. We have 4 moles of NO2 in the second reaction. So what you'll notice is that the stoichiometric coefficients have been multiplied by 2 when we go from reaction 1 to reaction 2, right? So reaction 2 is just reaction 1 multiplied by 2. All of the coefficients are double. So the K values in this case, you would square the K value given for K1, and that would give you the value for K2. And so you raise to the power, you raise K to the power that is equal to how much you multiplied it by when you converted one reaction to the other. So if reaction 2 is reaction 1 times 2, then K2 is K1 raised to the second power. Doubling a reaction means you square the K value. Any value you multiply the equation by becomes a power that you raise K2. So in other words, if you had multiplied the coefficients by 3, you would have cubed it. If you had multiplied them by 1/2, you would have taken the square root of them. It would have been to the 1/2 power. So that 2 is squared because if it's times 2, when you go from reaction 1 to reaction 2. Reversing a reaction inverts the value of K. We already talked about that. Adding reactions together means you multiply their K values. And finally, last but not least, multiplying a reaction by an integer means you raise K to that power. Okay, so let's just make sure we know how to do this with numbers. We have an equilibrium here, N2O4 forms 2 NO2. We have the equilibrium constant Kc, 4.64 times 10 to the minus 3. The temperature is given only because K depends on the temperature, so the temperature is often given. So let's start by figuring out what if we want to know the equilibrium constant for this reaction. So you need to look at the reaction and figure out how it differs from the one that you're given. The one that you're given it's in an opposite direction, right? So we've clearly reversed it. We've also multiplied it by 2, so we have double the coefficients in front of each value. So it's been reversed and times 2. So that means we need to do 2 things to the equilibrium constant. First, by reversing it, we need to invert the equilibrium constant. So that's the 1 over x button on your calculator. You get 2.155 times 10 to the minus times 10 to the 2. And we need to multiply it by 2. So that means we need to take our second reaction. Since that's times 2, we're going to square the equilibrium constant. And that's going to give us, so we're going to do 2.15517 times 10 to the second, and we're going to square that number. Then that's going to give us 4.64 times 10 to the fourth. So we did 2 things to the reaction, which means we did 2 things to K. Now the second example, we have 2 equilibrium reactions, and we have their corresponding equilibrium constants. It just says K1 and K2. If there isn't a value given, if it doesn't say Kp, then you should assume that it is a Kc. The C is sometimes just understood. So if we want to know the equilibrium constant for this reaction, then this is, if you go back to Chem 101 when we used Hess's law to manipulate reactions and then combine them to get an overall reaction, what you'll notice is that we have CO2 on the left side of the equation in our equation that we don't know the equilibrium constant for. And CO2 is in this first equation. So what I'm going to do is I'm going to take my first equation, reaction 1, and I'm going to invert it. I'm going to reverse it. So we're going to reverse reaction 1. That's going to give us this reaction. That means we're going to invert K, and that gives us, whereas we had a K that was very large, lies far to the right, when we invert K, it's going to lie far to the left. And that should make sense, I think. If this reaction as written lies far to the right to the CO2 side, it'll still lie far to the CO2 side even when we reverse it, which means it lies far to the left. And now if we take reaction 2 and we add that one to the reversed reaction 1, then what you'll notice is that you get the overall equation. So we're going to sum those two reactions. The sum of these two reactions is the equation we're looking for, which is this one up here. CO2 plus C goes to 2CO, which means that our overall equilibrium constant, and this is just proving that they add together, the O2s and one of the carbons cancels. So that means that K, our new K, is the product of these two Ks. So we're going to multiply 7.1 times 10 to the minus 70 times 1.2 times 10 to the 48, and that's shown here. 7.1 times 10 to the minus 70 times 1.2 times 10 to the positive 48 gives us 8.6 times 10 to the minus 22. And I circled that here. That's my final answer. It has 2 sig figs because both of these numbers have 2. And that's the final answer.